Okay. We also posted the proposal dates and the homework dates and so on. So I think the proposal is due in 2 weeks. So maybe start thinking about your project directions, come to office hours, talk to us, and you guys can try to find something exciting. And feel free to change it after, but good to start thinking about it now. Okay, let's get started. So today's structures, we're going to start by talking a little bit about just wrapping up our MDP formalism and why we should care, some applications that I think are exciting. We'll then start talking about imitation learning. Now, imitation learning is obviously not RL, but I think it's like a pretty important tool that lots of folks use today. And so we'll start with imitation learning. We'll talk about an algorithm called behavior cloning. We'll say why behavior cloning is not great, and then we'll try to think of some solutions to those problems, right? And then we'll talk about compounding error. And finally, we'll talk about, I won't get to this 100%, but we'll talk about some modern tools that people use with generative models that make imitation learning work super well. Okay. So just to recap, we introduced this framework of a Markov decision process. We have states, actions, rewards, and we'll have transition dynamics that are unknown. They obey the Markov property, and we'll use this notion of a trajectory, which is a state, action, reward, state, action, reward. And so that's going to be our formalism. Our goal is to find a policy. Policy will be a mapping from states to actions, which can be stochastic. And we want to learn the parameters of our policy that maximize the expected sum of rewards, right? Um, so that's the framework we're going to use. Now, why we should care, like lots of you have different reasons to care, but some things that I thought are fun about reinforcement learning is that think of like typical generative AI, generative modeling, right? Diffusion models or next token prediction or whatever. They're often about replicating the data distribution, right? And like maybe sampling some new things, but reinforcement learning is really about going beyond the data distribution. So like if done correctly, the hope is that you should be able to go and discover things that are like obviously nonsensical, like raccoon cooking or doing the dishes or whatever is obviously not something that's in the training data, but if you fine tune these diffusion models with RL, you often get interesting things. This is some examples of it being used for topology optimization. So like material structures and I think like there's been a lot of new work out of NVIDIA and other places. We had a faculty candidate actually give a great talk on using RL for test time training. And so you guys should go check it out. It's a great talk. Um, I'm a roboticist. I mostly care about robotics. And I think like where RL is really, really useful as opposed to other methods for robotics is in the presence of lots of contact. So if you have contact, it's hard to differentiate through gradient facts through them. So there's like robotics methods for planning and these kinds of things, but planning just like struggles whenever you have contact or discontinuities. And so reinforcement learning is a great way to kind of smooth over those discontinuities and get pretty contact-rich behavior like parkour or precise insertion or dexterous manipulation. So those two, the top two are examples from our group, and the bottom is from CMU, I think. And many of you are folks who are interested in language models. I think the two examples that are most prevalent are things like RLHF, where you can there's lots of nice explanations for why RL is a good tool for training language models as opposed to like offline methods like DPO. But maybe the most compelling one I've seen is from another faculty candidate we had, Gokul, which is on like the value of using this two-stage process of first training a reward model and then doing RL versus just doing essentially weighted supervised learning. So you guys should go read that. And then the second is like reasoning models, so things like DeepSeek and its many, many, many variants after that. And I think we don't have a great way of doing reasoning beyond RL. Like RL is the most performant way of getting reasoning, as far as I know. Right, so I'd argue that reasoning type models look a lot like model-based RL. So we'll maybe cover that, but overall, I think there's lots of interesting applications beyond those, right? So some of them like our kernel optimization or weather balloon navigation. There's some stuff from Mark Belmar that does that. Crystal design, chip design that Azalea and others at Stanford did. And so I think there's like lots of really cool applications. So I'd love to see more of these in the projects and so on. Each of them requires some changes. It's not just the same. Okay, so don't use RL for everything though. It's not just like a catch-all tool you should use for everything. So examples here are like aerospace. I don't know. I don't know if you want to fly your aircraft with deep RL or like have space flight or space debris caught with deep RL. I wouldn't do that. Things that are really, really repeatable. So if you want to do industrial robotics in a factory, you're manufacturing 10,000 things. I would like manufacture things very, very precisely and focus on planning and speed. And I wouldn't like try to do RL in those settings because there's like not enough variability to need it. And don't anything that you need some guarantees on. It's not the tool. But I think where it can be useful and yet to be proven is things like homes or offices or things like that, where like the stakes are not that high, but the diversity is super high. And so you want like high mix, low volume, basically. You want things where like data collection is not that expensive, the consequences are not that catastrophic, but you spend a long time in any one environment, right? So one way of thinking about it is RL is a great tool for overfitting. Like if you want to do overfitting in one environment, like this is a great tool to kind of use to do overfitting. So that's how I think about it. But don't just blindly go use RL on things. Okay. Overall, sequential decision making is a bigger space than just RL, right? So there's a bunch of nice trajectory optimization algorithms.
It's limited to relatively simple.
There's imitation learning, which we'll try and cover today. And then there's like things that are more unsupervised decision making, world models, if you will, or unsupervised reinforcement learning. There's things that go beyond like typical reward maximization. And so I think it's good to know about all of those, but we'll focus a lot more on reinforcement learning this quarter. Okay. So the general structure of what we're going to talk about is we'll start with imitation learning. We'll then talk about model-free RL. So we'll talk about policy gradient and then actor critic or approximate dynamic programming. We'll then talk about model-based RL, right? Like trying to learn a model and plan in it. We'll then try to like introduce the idea of inverse reinforcement learning, which is like trying to infer the reward function for RL, and try to unify reinforcement learning and inverse reinforcement learning using a framework called control as inference. And then we'll talk about some frontiers, right? So some frontiers is exploration, learning from prior data, learning multitask things, meta learning, like someone who's interested in. Like all of those kind of would be at the end, right? I can also change this because I'm making the lectures on the fly. So if there's anything that you feel needs more representation, just make an EdStem post or bother me about it, and we'll do it. Okay. Any questions so far? No? Cool. Let's get started with the imitation learning. Right? So, I stole this video from my student Kate. It's an example of Sai teaching the Gangnam style. Let's see. But a lot of behavior that humans learn, you could argue, is through imitation. Some of it is through reinforcement, but a lot of it is through imitation, right? And so you want to observe other people and be able to learn complicated things. And so the paradigm of imitation learning, put simply, is you're going to have people show you how to do things, and you want to copy them, not just in those scenarios, but in other scenarios as well. And so you really want to understand the intent behind what someone is doing, and then like generalize to new scenarios where they would do similar things. Okay, so the framework we're going to use is we're going to be given demonstrations of optimal behavior. So we're going to have states, actions, states, actions, states, actions. So you can assume that you have trajectories of near optimal behavior, right? So in the framework of imitation learning we're going to do so far, we're not going to try and be better than the expert. We're going to just try and match an expert, right? And so we're going to say these things come from an expert. We're going to say we have traces from pi star. And we're going to try and like match the performance of pi star, but we don't have access to pi star. We just have access to states and actions. And the other thing to note is that we do not have access to rewards. Okay, we just have access to states and actions, states and actions, states and actions. Right? Multiple trajectories. You can think of like me showing you how to pick up cups in 1,000 different places, and your job is to figure out how to pick up the cup in a new place. Right? So that's the setting we're going to consider. I'm just going to be a little sloppy with the notation in places, but we're going to like say that the states and actions come from pi star. But like you can think of it as like doesn't have to be truly optimal. It could be just like some expert, which might be a little noisy. Okay. And in that setting, our goal is to figure out a policy pi theta, figure out the parameters of a policy pi theta that matches the performance of the expert, right? So you want to like minimize the gap. If you remember like the J notation from last time, you want to minimize the gap between J pi theta and J pi star, right? You want these to be as close as possible. So J pi star is the expert's performance. J pi theta is your learner's performance. You want these things to be as close as possible. Okay, and so the idea in imitation learning is to, or behavior cloning specifically, is to treat the imitation learning problem as a supervised learning problem. Right, so you're going to take all of these sequences of trajectories or state action pairs that you get. You're going to like pretend that they were like XY tuples. So like if you think of any classification or regression problem, you can think of this as just like a bunch of XY tuples, right? At this state, you take this action. At this state, you take this action. At this state, you take this action, right? And then you just do supervised learning. Like you would do like any regression problem, or any classification problem, or anything like that. You're just going to treat it as a supervised learning problem and apply SGD, right? Just like plain old. And so the nice part about doing that is you don't need any rewards. You don't need any online experience. You're just going to take your offline data and treat it like a supervised learning problem. Yeah. And that's what you'd call behavior cloning, right? And so the reasons to do this is that it's like super simple. It's like dead simple, and you inherit all of the nice machinery of supervised learning from other domains, right? You can use your big transformers, and you can use your like great optimizers, shampoo and muon and this and that. It scales offline because you don't have to have interaction data. Right? And you don't need rewards. Rewards are a huge pain. And the cons here are that it does require expert data. So you still need expert data in imitation learning. It doesn't necessarily get better, right? Because it's offline training procedure. And we'll show that it like struggles as the horizon of the task increases. As you get longer and longer and longer, your imitation learning will struggle. Yeah. Okay, so the idea in behavior cloning is to treat imitation learning as a supervised learning problem. So you're going to take a sequential problem and then treat it like a non-sequential problem. Right? And so you're going to say, you're going to solve it with maximum likelihood, right? So maximum likelihood says, I want to find the parameters of a policy pi theta such that if I feed in expert states S star, I will produce expert actions A star with high likelihood. Right? And so the goal here is to do maximum likelihood supervised learning. If you think of like the policy class of pi theta as a Gaussian, this will become like an L2 loss. If you think of it as a discrete variable, it'll become like a cross entropy loss. Right? And so, but you're just going to treat it as supervised learning. That's it. So just like in any image classification, you want to like take in an image, output a class. Here you're going to take in the state of your system through whatever image slash state encoders, and you're going to output a distribution over actions. You're going to try to maximize the likelihood. The important thing is you're trying to maximize the likelihood of A star when you're fed in S star. Right? So the important thing is the training distribution is not determined by pi theta, like in RL. It is determined by the expert. Right? So when I say sampling from D, you can also think of it as S star, A star is sampled from like pi star. Right? So the important thing is you're sampling from pi star, not from pi theta. In RL, you are sampling from pi theta. In imitation learning, you are sampling from pi star. Okay, so the general paradigm of imitation learning is you get a bunch of experts who drive around and do things for you. You treat that as a supervised learning problem. You stick it into SGD, you get some parameters, and then you deploy offline. Then you deploy online. And so when I say deploy online, you're going to train this thing offline. You will get some theta, right? And then when you're deploying this online, you start with some initial state, you feed it into your policy. Policy gives you some sampled action A naught. You run it through your environment, it gives you S1. You run it through pi theta, it gives you A1, and so on. Yeah. So remember, you're training it offline, but you're running it online. At test time, you're going to run it sequentially. So you can just use it to control your robot just by like feeding in the current state into the policy, getting an action, playing the action, and repeating. Okay, so before I tell you what's wrong with it, any guesses? Why is this not a good idea? Quit is not allowed. Any any guesses?
Maybe just why not let them use that.
Right, like randomness of the environment is 1%. But I'd contend that's actually a bad idea even when the environment is deterministic. And so why so? Yeah.
It doesn't seem like we take into account the sequential behavior of doing it.
Exactly. Yeah. So you're taking a sequential problem and making it a non-sequential problem. And that's going to cause some problems. Yeah, good.
You might end up in a state where the expert never goes.
That's
and you
right.
don't know where to go.
That's right. Yeah, so that's basically the challenge with imitation learning. But before that, let's just look at like the code is super duper simple. Like, of course, there's like beefed up versions of this, but like that's all. It's just like a tiny snippet of imitation learning code. Right. So you can think of this as just like let's see which are the interesting parts here. Like you're predicting your action here. You're just like your criterion is going to be your log likelihood, and you're just gonna data load. You're gonna like compute your loss as your quantity loss as or your MSE loss, and just take gradients backwards. That's it. Like the training procedure is stupid, but the trick is in deciding the architecture, is dealing with this like sequential gap and like other things like that. So the general paradigm of imitation learning or behavior cloning is applicable across a class of different functions. We're going to stick with arbitrary neural net function approximators, but really all you need to do is like solve the maximum likelihood problems. As long as you can take gradients or something to solve the maximum likelihood problem, you can apply it across anything, right? It doesn't have to just be neural nets. And so, yeah.
And so in this setting, we assume the Markov property.
Yeah.
So then why would it matter if we're not treating it as a sequential problem?
I'll talk about it. Okay, so this is like not invented in the 2000s. It was invented back in like 1980s. And so there's some examples from 1989. This paper called Alvin, I think out of CMU, and Former came up with this, and they had like a tiny little neural net driving a car around with these with these kinds of visual inputs. But it was actually pretty good. Like it was able to drive around those streets and like do things that are reasonable. Of course, this is a cherry-picked video, but it's kind of cool that we were doing imitation learning in 1989 and we're doing imitation learning in 2026. But we've given it lots of fancy. But some examples in 2026 are, here's an example from Chung at Stanford, where he collects data this way. And then you can like get robots to autonomously do things like clean the dishes and so on in like slightly different configuration. And so the cool thing about this particular project is that he didn't have to like teleoperate the robot or anything. He just wears these gloves and he collects data. And that allows you to like transfer over to a robot. These are some examples from this company, Sunday Robotics, and another one, Generalist, where they show that if you scale up imitation learning with enough data, you can do pretty cool tasks like really precise manipulation or like sorting nuts and bolts and things like that. And so all of these are just largely imitation learning with lots and lots and lots of data. And some of the tricks that we'll talk about in today's lecture. But it kind of works unreasonably well, right? And so there's some reasons we understand. There's lots of reasons we don't understand. So I wouldn't say imitation learning is fully understood. But it does work unreasonably well. So if you were to start programming a robot, I would start with imitation learning. It just works the best. Okay. So remind me of your name. D? Okay. So as Dean was saying, like, why, if you're assuming the Markov property, why does this matter, right? And so the challenge is this challenge of compounding error, right? So one way of thinking about it is imagine that you had like an optimal trajectory, right? And you like made a little bit of a mistake and you trained it. And so it's like, epsilon good on the training distribution, but the epsilon is very, very small, but it's there, right? And so what's going to happen is like, if I just evaluated how good I am on these states offline, I'll be pretty good, right? My training validation loss will be low. But what happens when I apply things sequentially is that I'll do this. I'll have a tiny little bit of a mistake. And now my input is like a little bit different than my training set. And so I'll make a little bit bigger of a mistake. And my input is now a little bit different from my training set. I'll make a bigger mistake, right? So you start drifting off the training data.
That means that this problem is the problem of long horizon
That's
passes
it.
all boils down to what someone else said before about just being out of distribution of the space that you
That's right.
see in the expert.
Exactly. Right. So like the primary gap comes from the difference between training and deployment, right? So training is under this D, which is essentially under pi star. And deployment is under this D, which is under pi theta. right? So training is not equal to test. And machine learning, if training is not equal to test, then you're in trouble, right? And so the main way to think about it is the way I like to intuitively think about it is you're kind of on this tightrope, which is your expert data. And if you make little bits of a mistake, you fall off the tightrope and then you don't know how to recover, right? And so essentially you can show in a second, we'll show that it's like quadratic in horizon. So the longer your horizon is, the more chance you have of falling off the tightrope, right? And so you can think of it as like essentially a difference between the online rollout where you're evaluating things under the distribution of the learner, under the distribution of pi theta, and the training distribution, which is not under the learner, but which is under the expert pi star, right? And so the reason it's important to think about the expectations is this is under pi star, this is under pi theta, and we are good under pi star, we are not good under pi theta, right? Does that make sense? And so it's not just like an imaginary issue, right? If you look at some examples, even from Pomerleau's example, you'll see that it's like drifting off the road. And these are some examples down here from our group. We'll see that like over, actually Quinn might have shot this example, but over like some horizon, you'll see that there's like drift over time, and that leads to failures that get worse and worse and worse. So one useful thing to know is if you're doing imitation learning, like normally in supervised learning, validation loss is a great metric. Like if you're good validation loss, it's good. In supervised learning for imitation, if your validation loss is good, your policy could still be really bad. And so in general, it's not super clear yet how to measure a good metric for downstream closed loop performance. This is like an open question in imitation learning. Right, but don't just trust that my validation error, like it's a prerequisite that validation error should be low, but validation error being low doesn't mean that closed loop error will be low, right? And one way to think about it is that like, even if validation error is low, you'll still have small mistakes. And it really is about how your policy responds to those small mistakes, right? And so you could have something where you have like slightly higher validation error, but like the policy is like able to recover from going slightly off. And so, yeah, if anyone's interested, I think understanding a good metric for evaluating policy performance in closed loop is still a very open question. Okay, does it make sense? If it doesn't make sense, the rest of the lecture is not going. Questions? Thoughts? Feelings? Okay, good. All right. So, maybe one question we want to ask is like, as Dean was kind of getting at, like how bad is imitation learning? Like does it scale with horizon, right? And so one thing we can do is we're not going to do a full formal analysis. It's in my slides, but it's at the end of my slides because it's going to take too long in the class. But you could think of like having a 0-1 cost, which says the cost is 0 if I match the expert, and the cost is 1 if I didn't match the expert, right? And we want to understand what is the expected cost when you roll out the policy pi theta, when you trained on the maximum likelihood objective, right? So you trained on the behavior cloning objective, and then you roll out a policy pi theta, the same way, the sequential way that we are talking about. And we want to kind of measure how bad this cost is going to be, right? So you're trying to see, like, if I did behavior cloning and I had to say something a little more formal about like the incurred cost when I run something out online, like how bad is it going to be? So, like the way that I like to think about it is this tightrope example. You're on this tightrope, and if you fall off the tightrope, like the worst case bound is basically that I don't know how to recover, so I will incur a cost of 1 for every step thereafter, right? And so, if let's say that we had a policy pi theta, which has epsilon likelihood of making a mistake on the training set, right? So this is true when ST is sampled from pi star, right? And I could say that like on ST not sampled from pi star, like ST from let's say pi theta, let's say it could be arbitrarily bad, right? So it's arbitrarily bad. What you can kind of show is that let's say your horizon was H. If you fall off the optimal path, you will then encounter a cost of H from there onwards, right? So the first step, imagine I have an epsilon likelihood of falling off at the first step. And then if I fall off at the first step, then I will incur a cost of H, right? And then I have an epsilon likelihood of falling off at the second step. And then if I fall off, then I incur a cost of H minus 1. right? And so at every step, I independently have a likelihood of epsilon of making a mistake, which means I fall off the optimal path. And if I fall off the optimal path, I will encounter a cost of h minus 1, h minus 2. And when you sum that up, then you get like a quadratic cost, right? If you want a more formal proof, it's at the end of my slides. But you could show that behavior cloning in like a typical sense has a cost that grows with epsilon h squared, right? So that means that if your horizon is super long, your behavior cloning will be bad. And if you're underfitting, which means the epsilon is pretty high, then you'll also be bad, right? So you don't want to underfit and you don't want to have really long horizon. Now, one thing to note is it's a pretty conservative bound, right? Like I'm saying that if I like fell off, I don't know what to do, I'm like screwed forever. That's not always true. This is like a worst case file. Okay, but I'm mostly just using it as a way to motivate the rest of the algorithm. Don't worry about the proof too much. But the two things that we want to focus on is the epsilon term, right? And the h squared term. So the epsilon term is telling you, am I underfitting? Am I not able to match the expert? And the h squared term is the compounding error term, which says that I can't do long horizon problems. Okay? And so we are going to try and solve how to get epsilon to be small and how to reduce that h squared term to a not h squared term. Okay, questions? Thoughts? Yeah.
When you not in public more over like the space,
Yeah.
the performance of the imitation learning will get like better.
Yeah, so you don't want to keep collecting data in a very narrow regime. So the like typical wisdom is that you want to collect some failure data, some recovery data. So you want to collect data in a particular way, not just like, so this algorithm we talk about Dagger is collecting more data, but it's collecting more data in a particular way. And so it's not just the amount of data, it's like what states you collected on. Okay, so how are we doing on time? Okay, good. So we're gonna next think about solving these two problems. We're gonna try and solve the underfitting problem and the compounding error problem. So let's start with thinking about the underfitting problem. Okay, so we're all in the era of deep learning, right? And so our general wisdom is if you want to reduce the epsilon, just add more layers, right? If you add more layers and make the network bigger, then will we not just like drop epsilon, right? And so like if you look at scaling laws from language models and other things, like the arguments is just make the model bigger and your training loss goes down and you'll have nice properties. But what we'll find here in imitation learning is that it's kind of true, but it's not as simple, right? And so there's a little more nuance to it than just make your model bigger. Right? Making your model bigger does help, but there's a little more nuance to it. Okay, any ideas what the nuance might be? Yeah.
Like more data for bigger model.
Yeah, more data for a bigger model. That's a good point. The point that I'm going to get at in this next part of the lecture is that so far we've kind of like done behavior cloning under like the assumption of, let's say, like L2 regression on your actions. So like you're going to say like, I'm going to try and measure the difference between pi theta of s minus a squared, right? And so if you're in L2, you have a Gaussian. And if you have a Gaussian, we're going to argue that it's not expressive enough to capture your training distribution. So it's not just about functional expressivity, it's also about distributional expressivity, right? And so there's many different classes of function approximate or many different classes of distributions we could use, right? So there's categorical, things like a table. There's Gaussian, which is the most common thing that people have used for imitation learning, right? L2 regression. And then there's things like diffusion. Like we're typically gonna, like often behavior cloning had thought about doing things as a Gaussian. That's the like simplest, most prevalent way of doing things. But we're going to argue that maybe some of these other choices, which are a little more complicated in some cases, will be better at solving this underfitting problem. Okay. The fundamental trade-off though is like with categorical, which means categorical means you like have a table. What's the challenge with categorical stuff for like a robot? Why is it not what makes it hard to do? Yeah. You have a continuous space. You have to discretize it. And you discretize it across k dimensions. You have exponential number of bits, right? And a diffusion policy, one of the challenges, you don't have tractable likelihood, and that makes things a little messy. Plus, inference is slower. So there's like trade-offs that you like. Gaussians are good, but they will come with some errors. And so it's not just like slap the most complicated generative model on there. There's some trade-offs that come with it. Okay. So let's consider this maximum likelihood problem with a Gaussian policy, right? So what that means is like this pi theta is a Gaussian, right? So you'll have some x, whatever, x minus mu, something like that, right? So when you think of a Gaussian, you can kind of think of it as a unimodal distribution. And what happens in lots of real data, lots of data collected by people, especially when you do it at scale, is that you have multimodal distributions, right? So if like, imagine that you're this car, you're driving around this obstacle, some people will go left and some people will go right. And now the challenge with some people going left and some people going right and fitting a Gaussian to it is that you like go straight through the middle, right? And so Gaussian policies with the supervised learning objective will do mode averaging. And when you say something does mode averaging, if you have these two modes, both here and here, like we'll cover this in a little more detail next slide, but if you work it out, you'll see that you won't pick one of the modes, you'll try to cover both the modes. And there's no way for a Gaussian policy to represent both modes. And so you'll often get like weird behavior that is neither of the experts. And so one challenge is dealing with real human data, right? Like when we had synthetic data, it's not so bad. Like imagine if you're trying to do imitation learning with data generated from a reinforcement learning policy. Often the reinforcement learning policy will also be a Gaussian, and so you're fine. But with real human data, people are multimodal. People have hidden variables. Like there's lots of things that make things multimodal. And so whenever you're doing imitation learning, you want to not just consider is your model bigger, but you want to consider how expressive your model is distributionally, right? And that's kind of what leads to mode averaging. So we'll consider the obvious thing of going beyond the Gaussian, but we'll also consider different ways of like, solving this mode averaging problem. Okay, so if we have this objective, right? So you're trying to do maximum likelihood. What I'm going to try and do is express the maximum likelihood objective as a divergence. And if we write it as a divergence, then we can change the divergence measure and get like nice things out of it. Okay, so let's take this divergence measure. Or let's take this maximum likelihood objective. And we're saying S star and A star comes from D. D is coming from, let's say, pi star, right? So what we're going to do is rewrite this objective as an expectation of S star coming from d pi star, right? So it's saying states are sampled from the stationary distribution under an optimal policy. An expectation of A star coming from pi star of A given S star, right? Or whatever, A star given S star, of log pi theta of A star given S star. Yeah. So all I did is like, I iterated the expectation. And then what we're going to do is we're going to solve this argmax problem. So it doesn't matter if I add something that is not dependent on theta. So I'm just going to subtract log pi star of A star given S star. Yeah. So what I've done is I've expressed the expectation as this iterative expectation on states and then action. And then I just subtracted out a log pi star. Right? It doesn't matter. It doesn't change the maximum. So if you do those things, then you can rewrite this objective as a max over an expectation under S star coming from the distribution of the expert, A star coming from the policy of log pi theta of A star given S star minus log pi E or log pi star, right, of A star given S star. Right? We didn't change anything. We just iterated the expectation. We subtracted something that doesn't depend on theta. And now just by like some log properties, you can rewrite this thing as an expectation of S star coming from pi E, of A star coming from pi E, log pi E over pi theta, right? And so, and I changed the max to a min, so just flip the order. Okay, so the important, you could just say like log A minus log B is equal to log A over B, right? And then you like just flip the order by taking a negative, so max becomes a min. But the nice thing, how many of you are familiar with KL divergences? Ish? Okay, let's focus, right? So if you look at this objective here, the KL divergence between two distributions P and Q is the expectation under P log P over Q, right? And so if you look at this objective right here, right, it is literally the KL divergence between pi E and pi theta, right? And so what you can write this as is you can write this as essentially the forward KL divergence, right? So you can say the important thing about KL divergence is not symmetric, right? So the order matters because the order determines what you're taking the expectation under. So you can write this as the forward KL divergence between pi E and pi theta. And whenever you have a forward KL divergence with a underexpressive policy class, like something like a Gaussian, you're going to have mode averaging, right? And so an intuitive way to think about it is imagine you have like two modes, right? And that's in your data distribution. You're going to like eat a huge penalty if you miss any of the modes you can't change the data distribution. So if there's anything which is in here, but is not in pi theta, you're just going to eat a huge penalty, right? And so what you want to do is have no mode uncovered, right? And so you're going to try and cover all the modes so that you don't see, you don't have like pi theta be really small anywhere, right? And so one way of thinking about how to interpret this objective is that when you have the forward KL divergence, you're going to try and mode average. And with other divergences, you will not necessarily mode average. But really, you can't control the data distribution. So you never want to miss anything that is under the data distribution. Okay. So what we kind of showed here, just to recap, is we started from the maximum likelihood objective, behavior cloning, right? And we said that the maximum likelihood objective with a little bit of manipulation, you can write it as the expected forward KL divergence between pi E and pi theta, right? And so the argument here is that the forward KL divergence will lead to mode averaging. But in general, I think what this kind of gets us towards is that we define the forward KL divergence, but you can think of it as like a broader class of F divergences. Right? So you want to say there's a broader class of F divergence, and F divergence can be defined this way. So it's expectation Q of some function F of P over Q, right? And so if you have a broader class of F divergences, the argument is that you can change the divergence to see different properties, right? Okay, so the main thing I wanted to get here is that maximum likelihood is equal to an expected forward KL divergence. A KL divergence is a special case of a broader class of F divergences, right? And depending on what F we choose, we might get different properties. Cool. Okay, so if you believe me, then the question is, what different divergences will lead to different properties, right? And so we started with the forward KL, which is behavior cloning. But we said that this is a special case of a more general class of divergences. The one that's most commonly talked about is this thing called the reverse KL, right? So the forward KL, you can think of it as an F divergence with the F equals X log X. Right? So if you can say the F of X is X log X, you can plug this in, right? So if you literally plug it into here, you'll have an expectation Q of P over Q log P over Q, right? You'll have these two cancel out, so you'll get expectation P log P over Q, which is essentially the forward KL divergence, right? So if you plug in F of X equal to X log X, you will get the forward KL divergence. An interesting alternative, and with forward KL divergence comes like mode average. An interesting alternative to the forward KL divergence is the reverse KL, right? So the reverse KL is saying, like forward KL is saying, expectation is the KL between P and Q, let's say. Reverse KL is just the KL between Q and P, right? So forward KL is the KL between pi expert and pi theta. Reverse KL is the divergence between pi theta and pi expert. Okay, so you can get the reverse KL just by subbing fx equal to minus log x rather than x log x. You can kind of do it the same way. Expectation Q of x minus log P over Q. Minus log is 1 over. So you get expectation Q log Q over P, which is essentially the KL divergence between Q and P, right? So one way of thinking about this is the KL divergence between a distribution P and Q is expectation P log P over Q. And the KL divergence between Q and P is the expectation Q log Q over P, right? So the important thing between the forward and the reverse KL is that the forward KL has expectation under P and the reverse KL has expectation under Q, right? So in our case, what the reverse KL distribution is going to be, the reverse KL is going to be an expectation under pi theta of log pi theta by pi star or pi e, right? Versus in behavior cloning, if you remember what we had expectation under pi e of log pi e divided by pi theta, right? But the important part is that the forward KL divergence, the data distribution was from pi e. You had no control over the data distribution. And in the reverse KL, the data distribution is under pi theta. And you do have control over the data distribution, right? And so the cool thing you can show is that if I do have control over the data distribution and I'm unimodal, I have one mode, I will just pick one of the modes, right? I'll pick the mode that has the highest likelihood. And so because I'm basically faced with an impossible choice, what I can do is I want to move my pi theta likelihood to the things where I'll get the highest likelihood on the expert, right? And so often when you have a reverse scale, you'll say that it's mode seeking, and a forward scale will be mode cover. Right? So remember, a reverse scale is going to be d of q over p. Forward scale is going to be d of p over q. Okay. Makes sense? Seeing a little bit of lostness. Ask me some questions. Yeah.
How we can be to get like the highest one?
Yeah. Because basically, if I don't pick the highest mode, like essentially, if I look at the reverse scale, right, it's going to be expectation pi theta log pi theta over pi e, right? Like if I place likelihood on not the highest mode, I don't get the highest by e. One thing you want to remember though is like, you can kind of think of it as expectation under pi theta of minus log pi e minus the entropy over pi theta. So like this pi theta log pi theta term is kind of the entropy of pi theta, right? So I guess I'll amend my answer to say that you want to pick the highest mode, but you want to make sure that pi theta has enough entropy. So it's not always guaranteed to pick the highest mode if the thing doesn't have enough. Okay. Yes. Yeah. Reverse scale corresponds to reinforcement learning. So like the important thing is if you look at reverse scale, right, it's going to be expectation under pi theta of log pi theta divided by pi e, right? And so it looks kind of like, you can write this as expectation pi theta of minus log pi e plus expectation pi theta of log pi theta, right? And so this is kind of like an entropy term. And you can kind of think of it as like a reinforcement learning term where the reward is minus log pi e. So reverse scale looks a lot like reinforcement learning and forward scale looks a lot like supervised. Right, so the important thing is reinforcement learning takes data under your own distribution, whereas imitation learning takes data under the expert's distribution. And so the right analog for reverse scale is reinforcement learning. Yeah.
So basically, the node you will choose is the one with the biggest measure.
Yeah. So it's not just the highest, but the one with the biggest. Okay. And then you can come up with all sorts of other fun divergences, a chi-square divergence or a Jensen-Shannon divergence. You can the nice thing about this framework, which actually one of my former students developed, is that you can kind of think about you can think about a more general class of imitation learning problems, but just by changing this divergence between all the sets of divergence measures that we have. Right? And so if you wanted to get imitation learning with the Gaussian to be better, you could try doing it with a different divergence. So like imagine that you had the problem where you are going left or right, and you are having mode averaging with forward scale and a Gaussian. If I did reverse scale, the right solution would pick either this or this, right? And so you can fix imitation learning either by using a different F divergence or by using a different distribution class. So don't use the Gaussian, right? Don't use the unimodal class, but try to use a more rich distribution class. Okay, so those are the two fixes. We are at 12:45 or 1:45. Let's take a 2-minute break and we'll return for the rest. But yeah, I'm a little tired. Just like feel free to walk around, we'll start it. Is this stuff you see all this? What? Yeah, bro. So usually when you said assume it's a 5. So it is like a 5E that is good on the first stage. So this is like fully clear. But if like many practice rates of 5E, one of the challenges with university is 5E doesn't have full coverage. Why is this converged? Yes.
I'm thinking of course it was I think that's how I was thinking about the discount. I'm thinking I want to this discount on either process
Yeah. Well, actually, I did say that before, right? You came in a little. Send me an email. I met with some people that are wrong. And send me an email and yeah, I like it. But I want if you really want to take it with me. Yeah. Is it all the
Yeah.
Oh, let me explain that. What does it mean to be cancelled?
Or under an expectation.
Expectation is P of f of x, right? Oh, you can think of it as an integral P of x.
Yeah.
And so what I had written was, for instance, expectation P of like when you do the forward scale divergence, x log x, right? So what you can write this as is like P over Q, P of x over Q of x, or I think Q over P of x. Q of x over P of x. Log Q of x over P of x. Yeah. Now like write this in integral form. So you can write this as P of x.
Oh, sure.
Q of x and P of x. Log whatever is this.
Okay.
It's just a little shorthand.
Yeah. Okay. Thank you so much.
Sure. Okay. Start back up. All right. So let's get started by first thinking about how to change our F divergence, right? So we said we're going to change our F divergence from the forward scale to the reverse scale, let's say, right? And the reverse scale will be mode CK. And so why might it not be trivial to change from the forward to the reverse scale? Like what makes it maybe harder? So remember, let's write it down just for posterity. Forward scale is expectation pi theta. Expectation pi expert of log pi expert by pi theta. And reverse scale is expectation pi theta of log pi theta by pi expert, right? Yes. You have to sample, well, in the forward scale, you have samples from the expert, right? So in the forward scale, this is forward scale, and this is reverse scale, but you're getting at the right thing, right? So in the forward scale, you have offline data from the expert. In the reverse scale, you have to sample from the expert, right? So one issue is sampling, right? Sampling from pi theta. In some cases, okay. In other cases, you have to run the thing in the world. It's kind of big. What are the other issues between this and this? And remember, you're trying to like minimize these divergences with respect to theta. Yep.
still sample from the answer and use like important weighting. Again.
Yeah. It's a great question. Your importance weighting distribution has to have coverage. So if it's okay if you're with importance weighting, you need to have overlapping support. Right? So if you have like overlapping support, then you've like seen that distribution somewhere, right? And so you've seen samples in that distribution already. But if your things typically they won't have overlapping support, like the expert would not have seen something that's slightly off. And so then you're in trouble. It's a good question. Okay, so the first is sampling, and the second is basically that if you look at this objective, you need to know the likelihood of the expert by E, right? So in this objective, basically you can break this down as expectation pi E of log pi E minus expectation pi E of log pi theta, right? And so if I'm trying to like minimize these with respect to theta, this term goes away. I don't actually care in the forward KL, I don't care about the knowledge of pi E. I don't need to know the likelihood under the expert. I just need samples from the expert, right? I just need to have samples from the expert. But in the second term, you can write this as expectation pi theta log pi theta minus expectation pi theta log pi E, right? But theta is in both terms. So I can't remove any terms, right? And so like the important thing, theta determines the data distribution here. Theta determines both the inside and the outside here, right? But the important thing is I cannot remove this term, which means that I need to know the likelihood under the expert, right? So I need to know log pi E. And like if I was a human, like what is a human's log pi E? I don't know, right? And so the tricky thing with the reverse scale objective is that you need to know pi E and you need to do sampling, right? So it's a nice to have, but it can be difficult in many cases because you need to know the likelihood and you need to do sampling, right? And so typically what you'll do is you'll like the sampling thing is still more solvable. In some cases, you're okay taking samples, but with a human, I just definitely don't know pi E. I only have samples, right? And so what Kay, my student, did in her paper, which is fantastic, by the way, you guys should go read it, is she showed that if you have like an arbitrary F divergence, right, including the reverse scale, you can like construct an adversarial surrogate objective that gives you the same optimum, right? So what she showed, and the trick is to use the convex conjugate for an F divergence because the F is convex. But you can show that like any F divergence, you can convert into an adversarial objective, which doesn't need to have pi E. You just need to have samples from pi E and pi theta. Right. So the tough thing about this objective is you need to know the likelihood. You need to have some function which tells me that this is the likelihood an expert would have given for this particular state. The nice thing about this objective, yeah, it's a GAN and all the other stuff, but you never need to know the likelihood. You just need samples. Right? And so the cool thing about this objective is that you like converted this thing where you don't know pi E into something where you just need samples. That's why it's neat. But I'll assign it as one of the readings for the seated paper discussion. It's a nice paper. Okay. So what we kind of got to is that other divergences may be better than the forward KL, but it comes with other challenges. Like for instance, you need to like know the expert likelihood. And even if you use this approximation, you have to solve a GAN, you have to solve this adversarial problem. Yeah, tough. So the solution that most people use is a simpler one, right? Which is to go from a Gaussian to a not Gaussian, right? And so to say, okay, Gaussians are bad, let's go beyond Gaussians and let's try to like make things a little more tractable. Okay, and so the next idea we're going to think about is that we're going to use a more expressive class of probability distributions, right? So we have a bunch of different choices here. The first is a mixture of Gaussians. The second is like a latent variable model, so like a conditional VAE. The third is autoregressive discretization, which is a kind of fun idea. Diffusion models, et cetera, et cetera, et cetera. Basically, copy paste, take your favorite generative model, slap it into imitation learning, and it kind of works. And then you get like 5,000 citations. The age for that has passed, but 2 years ago, if you did that, you would get a lot of citations. So, okay, let's think about a few of these choices and what it might comprise, right? So the simplest is to say, if I had a mixture of Gaussians, right? So if I went from one Gaussian to like a mixture of Gaussians, so a mixture of Gaussians can be thought of as distribution that looks something like this. It's parameterized by, let's say you had k Gaussians, right? Each of them is parameterized by a mean, a covariance, and a weight matrix, right? So or a weight vector. The weight vector sums to 1, right? And you have your mean and your covariance. And the whole point is that a Gaussian can represent this, and a mixture of Gaussians can represent, more complicated functions. Right? So if you have an infinite mixture of Gaussians, that essentially becomes like a VAE in some ways. That's an infinite mixture of Gaussians is a VAE, but as you increase the number of Ks, you can represent more and more complicated functions, right? And so it's a pretty reasonable thing to do. And the nice thing about a mixture of Gaussians is that you can compute closed form likelihood, right? Like this thing is like, the likelihood as opposed to some of the other models. The challenging part is it doesn't seem to work that well empirically, and it's hard to choose the number of Gaussians correctly. And so mixture of Gaussians were great in 2016, 17, but basically no one uses it today. Okay. The second thing we'll talk about is this idea of autoregressive discretization. And so the nice thing, basically the autoregressive discretization is relying on the idea of categorical distribution, right? Categorical is like a table, right? So if I have a table, the nice thing about a table is I can represent any distribution with a table, right? There's no unimodality or anything like that. But the challenge with doing this for a robot, let's say you have a humanoid, right? 40 degrees of freedom. Each degree of freedom, it's a continuous space, you need to make it discrete. So each dimension you spin into 100 bins, and then you have 100 to the 40, right? And that's that's big. So the challenge with representing something as a categorical distribution, like a language model, for things like robots and so on, is that the number of bins or the number of categories you have blows up exponentially. Right? And so this idea of autoregressive discretization may be kind of obvious in hindsight, but it's cool when it came out, which is to use the chain rule of probability to bin things dimension by dimension. Right? So it's kind of saying that imagine I had imagine a robot with 3 joints. Okay, so I had A1, A2, A3. And I can write this as P of A1 times P of A2 given A1 times P of A3 given A1 and A2. Yeah. And so now what I'm going to do is I'm going to treat each of these like a table. Right? I'm going to treat each of these like a categorical distribution. And then what I'm going to have is I'm going to think of this as one table on A1. Okay. I'm going to sample from that table on A1. I'm going to stick it into a neural net, and then I'm going to get a table on A2. I'm going to sample from that distribution, and I'm going to stick in the output from A1 and A2 into another neural net. I'll get a table on A3, right? But the number of bins that I have, it grows linearly, not exponentially, right? And so the nice part about it is that normally you'd have let's say you had B bins and D dimensions, you have B to the D. The nice thing about autoregressive discretization is you have B times D, right? And so that's going to scale a lot better. So one way to think about it is if you're just using the chain rule of probability, so you think of 3-dimensional action space as being broken up into A0 given S times A1 given S and A0 times A2 given S and A1 and A0, right? And for each of them, you just have a feed-forward neural net that outputs a vector of D or P dimensions, right? And so you can think of it as a transformer, an LSTM, or anything like that. But you take in your image, you produce the first dimension, then you sample from it, then you produce the second dimension, then you sample from it, you feed it back, and you produce the third dimension, right? And so it scales any sequence model would, right? But the key is that you're not getting exponential bins, you're only getting linear bins. What's the con? Why is this not always great? You have to choose the order of the dimensions, yeah. Other challenges.
Might be a better approximation for the joint space.
Exactly.
If in the best order,
Yeah.
might be a better.
Yeah. It could be a bad approximation for the entire joint space. You also lose some granularity as soon as you discretize. Someone else had the hand up? Yeah.
Neural nets introduce error.
Sorry?
The neural nets introduce a small epsilon error.
The neural nets introduce some, so you could have compounding error the same way, for sure. I guess the other thing is you have to run k forward passes through your model, right? And so it's slow because every time I like decode a dimension, I'm doing it dimension by dimension. And so for those of you who are interested in history, there's this like line of methods called pixel CNNs and pixel RNNs where you generated images pixel by pixel by pixel. And it's like infinitely slow. That's great, but it's like super slow. And so it's the same failure mode as you. With action dimension, it becomes really, really slow. But you should try it in your homework. And it's kind of fun. The most popular class of methods recently are these like diffusion models, right? So we'll cover this in more detail in a later lecture, but the idea of a diffusion model is to kind of think of a process that goes from data to noise, and then you have a reverse process that goes from noise to data. And the nice thing about that process is that you can represent multimodal distributions really nicely. And so you're not committed to a Gaussian or anything like that. Each step is a Gaussian denoiser, but like over many, many steps, you can have things that are very non-Gaussian. And so the cool thing about it is when you apply it to robotics, this is some work out of Sharon's group at Stanford. You can do like pretty cool tasks which are quite multimodal. So this is an example called push T that folks you often use, or like spreading pizza, things where people have many different strategies. And so initially it is thought that this does really well because of multimodality, like diffusion models are good for multimodality. But recent work has shown that it's more than just multimodality, and we'll cover that on Monday probe. The 2026 version or 2025 version of this is like flow models, right? Flow models, go ahead. Yeah.
What are the colors and the dots representing the operator?
Oh, yeah. So the colors and the dots there are like, so the idea of a diffusion model is you start from noise, and you denoise to like data. Right? So anytime you want to do sampling for the model, you start by like sampling noise, and then you denoise to action. Right? So here what you're going to do is you're going to sample basically random assets. And then you denoise to like the sequence of actions that you do. So like the colored dots there are like the initial guesses, and then the process that moves them is like the denoise. It's like a stylized version. It's not exactly. But you can think of it as like every time you want to generate an action, you don't just like feed state into your neural net and you output an action. Instead, what happens is you feed state into your neural net, you output like a velocity field. And then you start from a random action, and then you denoise that random action to a good action. And you train the model so that the denoising process is good. Right? And so the cool thing about diffusion models is that you can like, it's a very simple tractable objective to train this denoising process to represent non-Gaussian distribution. And flow models, I won't go into too much detail, but they're like a nicer version, easier to use version of diffusion models that are deterministic, or like the mapping is deterministic. And like some folks like physical intelligence use this to do like really high dexterity problems. It tends to be a little more stable and scalable and steerable than diffusion models. Okay. But if we revisit our map, we've talked about underfitting, right? And there's two ways to solve underfitting. One of them that I know of, one of them is a richer policy class, right? So you can use diffusion models or flow models or autoregressive or mixture of Gaussians, or you can use an alternative divergence, like a reverse scale or things like that, which don't do mode averaging. The challenge with alternative divergence is you have to like deal with the need for expert likelihoods and sampling and those kinds of things, right? So what we've covered so far is behavior cloning should be really bad. Because of epsilon and 8 square, we have some ways to make epsilon smaller. Yeah. Cool. Questions? How are we feeling? Pretty good? Confused? Okay, maybe hands up. You feel pretty good to keep moving. Great. That's the only answer that works. So it's great. So, okay, let's think about compounding error a little more in detail, right? So we've kind of like have this figure of compounding error. You make little mistakes. Those mistakes keep getting bigger. Gets worse with 8 squared. And so if you, so this is an example I really like from NVIDIA back in 2016. And they were like trying to do autonomous driving. And so they're trying to do autonomous driving. They're trying to do behavior cloning. They had a bunch of people drive their cars. And when they like started running it, they had some like slightly catastrophic behavior. And so they were doing a behavior cloning on cars in Santa Clara. And so this is what some of their experiments were. And so not so different than Tesla Autopilot, same vibes. But you can see that it's like pretty unreliable. It's drifting a lot. You like a lot of the compounding error issues are showing up, right? And then they like made a few small changes, something that I thought was really clever. And that resulted in significantly better performance. I mean, a lot less drift and a lot less like catastrophic events. Now, of course, this is cherry picked. No one is self-driving in 2016, but it did seem to do a lot better. And I thought the trick was really cool. So let's think more about how they did it, right? So the key that they did was actually a small hardware change that led to a big impact, right? So normally you'd have like one camera faces forward, and then you label the actions as your throttle and your steering, right? And they recorded the camera, the throttle, and the steering. And all they did is they added two more cameras, one that faces like slightly left and one that faces slightly right, right? And what they did is they said like, okay, the center camera is what it is, but the left camera, you point it towards the right, and the right camera, you like if you take the image from the left camera and you label it going towards the right, and you take the image from the left camera goes towards the right, and the right camera goes towards the left, right? So it's kind of like thinking of it as like the main line is what it is, but imagine that your car, which is facing this way, is actually now facing this way. Well, what I should probably be doing is turning my wheel back to the center, right? But if my car facing this way is going this other way, then what I should be doing is facing back to the center, right? And so essentially what they're doing is they're just like data augmenting. So you have the same image in the middle, and you just add something from the left camera going to the right and the right camera going to the left, right? And the assumption is that people are not going to drive into crashes, but instead you're just augmenting your data set so that you have like corrections. And so the neat thing here is that if you have corrections, imagine that you had compounding error, right? So your like car is going, and then you like drifted off a little bit, right? But now I drifted off, but my right camera had a label which is going to the left, right? And so I kind of know that I should be self-correcting. And so it never allows your car to drift off very much off the path. And so it makes that quadratic error not that bad, because when you fall off the tightrope, you have a label to correct yourself back on. And so I think that nobody uses that general principle or nobody uses that specific principle because it's like only works on cars. But I think the general principle is a reasonable one, which is to say like, if I can like find ways to like recover, and if I get data that is able to recover when I fall off, then I will never drift off that far, right? And so the general principle behind dealing with compounding error in many ways is to try and find recovery data, like data that says that if I fall off a little bit, I know how to get back, right? And so basically all the ideas we're going to think about in the next bit is like corrective labels that bring you back to the data. Okay. And so there's a nice paper called Data as Demonstrator that you might enjoy. They did it for dynamics models, but it's the same principle. It's basically saying that if I have compounding error, so like the dotted line here is the path that I want to follow. The solid line is the path that I end up at, right? And so what I want is data that takes me from x1 hat back to x2 or x2 hat back to x2. Okay? So you want data that does recovery or solves things on like states that are not just the expert. And so people have used that idea in many different ways, and we'll cover a few. But that's the key. Okay, so one way to think about it is that you know your fundamental issue in imitation learning is coming because you trained under pi star and you're deploying under pi theta, right? And so your data is under pi star, p data is pi star, and p rollout is under pi theta, right? And so there's a train test mismatch. And so the simple way of thinking about it is machine learning train test mismatch is bad. Like, can we just make the train equal to the test, right? And so there's this seminal paper at this point, which is called Dagger from Drew Bagnell and Stefan Ross. And their idea was to just say, can we make p data equal to p pi theta, right? So can we just make the train equal to the test? Okay. And so the idea is like dirt simple. So instead of trying to be clever about fancy recovery and this and that, right? Like all they're saying is this, like, try to aggregate data by running your policy and add that back into the training data set. And that's going to help give you recovery data, right? So it's a little more nuanced to it. But the idea of data set aggregation is as follows. You're trying to basically make p pi theta, which is like your rollout distribution, and the training data the same. So what you're going to do is you're going to start by you're going to start by like training by theta on expert, right? So behavior cloning. You're going to do supervised learning behavior cloning. So you're gonna train behavior cloning. It's gonna have some drift, okay, as usual. And what I'm gonna do is round one, I'll train offline, and then I'll run my policy online. Right? I'm gonna run my policy online to get samples from p pi theta. So I start by training on p pi star, right, on the expert. Then I run my policy online to get states and actions from p pi theta, run my policy. And then I'm going to ask the human to provide me expert labels on the states that are drawn from p pi theta. Right? So you can say that like, okay, I drifted off here. I'm going to have a human come in and label all of these with expert data. Right? And so the trick here is that all you're going to do is you're going to train offline. You are then going to run your policy. Oh, no. You're going to train offline. You're then going to run your policy in the world, right? Run the policy in the world to get trajectories. Those trajectories could be messed up, right? And they're going to be all the mistakes that you're going to make because of drift, right? And then you're going to have a human label those. So you're going to throw away the actions, right? The robot took actions under pi theta. I'm going to throw away the actions. I'm going to have the human label what they would have done at those observations. And then I'm going to throw it back into the training data set and repeat. Right? So I'm going to do an online learning like procedure where I like keep aggregating data. It's called Dagger because data set aggregation. You train, you run your policy, you ask a human to label the states that were visited by the policy. You add it back into your data set and you repeat. Yeah.
Very expensive dance in a way to deal
There's no adversary. So like all you're doing is it's closer to online learning in the sense you have like data that keeps coming in and you just like keep collecting data from your latest policy, feeding it back in. So it's kind of like the way I like to think about it is like you're whack-a-moling your errors. Right? So you're like saying, okay, I like trained on this. I will have some errors. I'll have the human fix those errors. So I've pushed those errors down. I might have some other errors the next time, but I add those to my data set, push them down until I have no more errors. Right? And so you show that converges to something that has no regret. And so, yeah, so it's not GANs because it's not adversarial.
Let's say all those layers learn how to recover, just add data on how to recover from
Right.
it.
So recovery is a bit of a overloaded term. Right?
Yeah.
So actually what we do in original Dagger is we just ask the human to label expert behavior. So like here's maybe the difference, right? So it's let's say this was where you were, and maybe like let's say you wanted to get here, okay? And like let's say you drifted off here, right? So maybe one way of doing recovery is like coming back to the expert data. And not, but like what Dagger suggests is that you just try to demonstrate something optimal, right? And so it's like slightly different, but related. Okay, but the key idea is like the reason Dagger is so popular is because it's dirt simple, right? It's basically just train your policy on the offline data, run it, have the human label optimal actions on that expert data, add it back to your data set, repeat. That's it. Supervised learning is the subroutine. There's no other fancy. Yeah.
If they can adding the correct labels back to the
Correct label. Yes. Yes. So you're adding the correct label, you're adding them on the states where the policy is making mistakes. Right? And so the point is that like you're not adding them everywhere, right? So if you like, I'm not just adding data here. I'm adding data in a particular thing where the thing is making mistakes, right? So I would like the point is that if I add data where the thing is making mistakes, then I like never have to waste. I never have to like waste samples for adding them. So one important thing about Dagger is that if I had a budget of data to add, like I would rather add data on the things that I made mistakes on than add data in arbitrary places, right? So one way to think about it is like someone asked the question of like, do I just add more data? It's like add more data, but add more data where the policy is making mistakes. Cool. And so these folks are roboticists, so they kind of went and applied it to some cool problems in drone navigation, like 15 years ago, but it tends to work pretty well, just because it's largely supervised learning. Okay, but obviously Dagger is not what everyone uses right now. What are some challenges, right? So let's okay, actually, before we get to the challenges, I did want to cover one thing. Okay, so one thing that like the LLM enthusiasts might be thinking about a little bit is this idea of on-policy distillation that's been popular in the last year. And on-policy distillation is very related to Dagger, right? So remember, Dagger is train, run rollouts, label with an expert, add the data back, repeat, right? And so what on-policy distillation does is it does Dagger, but it's doing Dagger for distillation between a student and a teacher, right? So like think of it as like you have a big frontier LLM and you want to distill it into a small LLM, right? And so what you're trying to do is student-teacher distillation. Your student is much less expressive than your teacher, right? And so what on-policy distillation does is it says that you're gonna try to do Dagger, but it changes because you don't just have access to sampling from your expert, you actually have access to the full likelihood distribution from your expert, right? And so we're going to combine some of the ideas that we talked about in this class. Dagger looks like this, right? You're going to like have green, which is where you were supposed to be, and red is where you went to, and the arrows are the labels from the expert. And the objective looks something like this, right? So you're going to sample states under your current policy, you're going to label them with the expert, and you're going to maximize likelihood. What on-policy distillation looks like is that you, at those states that you visited, the mistakes that you made, you don't just have access to a single sample, you have access to the whole distribution. And so I have access to the whole distribution, then I can use a different divergence measure, right? And so I no longer have to just do maximum likelihood. Like this, this Dagger thing does maximum likelihood. But the cool thing about on-policy distillation is that I can sample states from my learner. It's going to make some mistakes. But then I can minimize the different, that is definitely min, sorry. But you can minimize the divergence under a different measure, right? And the cool thing about this particular setting between a student teacher is that you know the likelihoods for both, right? And so there's no like likelihood problems like we had earlier. The cool thing is that if you have the whole likelihood, then you can get, the way to think about why it's intuitively good is that you don't have to fit all the modes anymore. You can just like fit a simpler thing because you are choosing your divergence measure to be reverse scale, right? And so people have been using this in language models a lot. And so you can see that like LoRa and SFT is kind of in blue. And you have like this on-policy distillation giving you a lot better performance on these like math problems with a lot less model parameters. So I wouldn't say I'm an expert in this. We can unpack it more, but the general vibe is like do Dagger, but do Dagger when you have access to the expert's entire distribution. And then don't do forward scale, which is maximum likelihood, which is what Dagger does, but do reverse scale. And so, yeah, that's the key principle. Okay, I think we are at 2:20. So let's wrap up today and we'll cover the rest of Dagger on Monday. All right, thank you.
Question.
Yes.
That I don't like the, that's it for class.